All right, so we're continuing our discussion of exponential and logarithmic equations. Today we're going to look at equations involving exponentials and equations involving logarithms. So this is section 4.4, solving exponential and log equations. All right, so we got 3 different methods for exponential equations and at least 2 methods for logarithmic equations. So the first method when dealing with exponential equations, for a really simple example, let's say I put 2 to the x equals 2 cubed, and you're asked to solve for x. That's hopefully the most straightforward, simplest example. Notice we got the same base. If this equation is going to be true, then obviously the exponents have to be the same. So we just equate the exponents and we get our answer. So this is what we call the same base approach. And again, this is the simplest idea of this. We'll look at some that are a little bit more involved. But this is what we call the same base approach. If we can, since it's an exponential equation, we're looking at an exponential equation, the unknown is going to be in the exponent. So if we can create this situation where we have the same base, any base, as long as it's the same, and if it's equal, and that's all that's on this side is a base raised to an exponent and a base raised to an exponent, then the exponents have to be the same. So we set the exponents equal, and it's not always just going to be x, it might be 2x plus 1 or some function of x that we have to then solve using techniques from previous chapters. So same base approach as an if-then statement is going to be if we can create the same base and different exponents, then the exponents have to be the same. Okay, that's basically the same base approach. So stepping up a level or 2 of difficulty from that first example, let's look at, if I say 4 raised to the x plus 2 equals 2 to the third. All right. So here we don't have quite the same base, but we notice that we can make that base into a base of 2. Right there, I can rewrite this as 2 squared. So I can rewrite this as 4 raised to the x plus 2 equals 2 to the third. And now, since we're working with exponents, we have to recall our properties of exponents, right? When we raise a base to a second exponent, we multiply those exponents together. So now we're going to multiply that and get 2x plus 4 over here. And now we've created the if statement that we want, right? So in the first example, the base was already the same. Here we had to do a little bit of in-between work to get the bases to be the same. Once we have that same base, now we can go to the then statement and equate the exponents. Okay, so if this is true, then this has to be true, must be true. And now it's just a simple linear equation. We remember how to solve these. We'll subtract 4 from both sides and get our answer. And we can always check that, right? Put that back into the equation and make sure that we get a true answer. If you put this back in here, you should get a true statement for that. So that's the same base approach. Let's look at one more of these just to make sure we got it down. Sometimes you have to change both bases to get a same base. Let's look at one of those. All right, so this is an example of another exponential equation. Let's see here, 4 to the x minus, let's make it 4 to the x minus 3, just. This is a checkpoint in the book if you want to check it later. It's part B of checkpoint 1. And that's on page page 480. Part B, page 4. All right, so whenever you have an exponential equation, whenever the unknown is part of the exponent, this is going to be your first choice to solve. It's not always going to be possible, right? Sometimes we can't create the same base, and we'll go to another method when we get to that case. But here we want to look at the 8 and the 4 and ask ourselves if there's a base that's common to both of those. Well, first you look at the lower one, right? You say, well, it's a to the power of 4. That would be the easiest case, but that's not true, right? 8 is not a power of 4. 4 squared is 16, so we can't do that. But 2's again, right? 2, I can write this as a power of 2, 2 raised to the third, and I can write this as a power of 2, 2 raised to the second. So that's what I'm going to do. Instead of 8, I'm going to write the number 8 as 2 raised to the third, and then that is going to be raised to the x plus 2. And over here, 4 is 2 squared, so we're going to raise that now to the x minus 3. So now we use the same property that we used in the previous example. We're multiplying these exponents together, so we get 2. And another common mistake is forgetting to distribute. A lot of people will put 3x plus 2 here. Got to remember that you're multiplying the whole thing. So 3 times x and 3 times 2. So we get 3x plus 6 on this side and 2x minus 6 on this side. Okay, so now if this statement is true, this statement is true only when these exponents are the same. So now we set those exponents equal to each other and say 3x minus 6, when does that equal 3x plus 6? When does that equal 2x minus 6? We know how to solve a one variable linear equation. We'll subtract 2x from both sides and get x plus 6 equals negative 6. And then we're going to subtract 6 from both sides and get our answer of negative 12. All right, so that's the same base approach. So we looked at a very simple example where the bases were already the same. That was the first one we looked at. Then we looked at one where we had to change one of the bases to get the same base so that we could use this approach. And then we looked at a case where we had to change both bases in order to use that approach. So that covers the same base approach. We said negative 12, that's the correct answer, very good. All right, so now when we can't do this, there's going to be cases where this is just not possible, right? We can't come up with the same base for both sides. But never fear, we have techniques to cover that situation. And this is when we use logs. Okay, so we're going to use logs to solve exponential equations. All right, so recall the relationship between exponential form and log form. All right, we said if y equals a base raised to an exponent, then that base is the base of the logarithm. The exponent is the result, and this is the exponent that we put on this base to get this result. The exponent that we put on this base to get this result. All right, so this is the idea that we're going to use to solve these equations. So let's look at number 28 on page 490. And this is an exponential equation. 28, we said, is 19 raised to the x equals 143. Okay. So not only this rule, now that I'm looking at this one, not only this rule, we have to remember here, we got to remember our basic rules, our properties of logs. When we have same base here, we know the answer is just the exponent. So what we're doing, and remember the log without a base is log 10, and ln is log base e. And again, these are the ones we have on our calculators, so that's why we like to use those. So here, we can't create the same base. You can look at 19 squared and see it's not going to be 143, so you can't use the same base approach. So what you're going to do here is you're going to take logarithms of both sides. So another idea that we're using here, we're saying that if we have an equation, then if we take the logarithm of both sides, either log base 10 or log base e, it's still going to be an equation. Right? We can take the logarithm of both sides and we still have an equation, either log base 10 or log base e. So we'll take log base 10 in this case of both sides. Okay, so notice no base written, that means log base 10. Now we're going to use this idea that we said was the power rule. We call the power rule. So we're remembering all our properties of logs. This can come into play sometimes. This is a very useful property. We're always using log base 10 or log base e when we're working with our calculators. And we want to remember our product rule, quotient rule, and power rule in this case. Remember the power rule said if we have something raised to an exponent, the logarithm of an expression raised to an exponent, we can take that exponent and bring it out in front and write it like that. That's what we're using here to bring that x out of the exponent. And now it's no longer an exponential equation. That's the idea. At this point, it's an exponential equation, right? The unknown is in the exponent. So what we've done by taking logs of both sides is we can now bring that exponent down, and now it's no longer an exponential equation, it's just a linear equation, right? This is just a number, this is just a number. So all we're doing now is solving. That, get your calculator. And you just plug that into your calculator, and I don't have an answer written there, let's see what we get. And these are always nicely, easily checked. Once you get the answer, you plug it back in here and make sure that it gives you a correct answer. Again, we should get an answer here somewhere between 1 and 2.
1.69.
Closer to 1. What is it?
1.69.
1.69. Okay, so then if you raise 19 to that number, depending on if we round it at all, you'll get something very close to 143. All right. So that is an example of using logs to solve an exponential equation. We started with an exponential equation. We took logs of both sides. Now at this step, you could have taken ln of both sides. It works just as well, again, because those are the only ones we have in our calculator. So at this point, you would have natural log of 143 over natural log of 19, and you would get the same number as we got there. All right, so that's one example of using logs. Let's look at another one here, number 34. I put my calculator in my backpack. I don't know if it's in my office. We'll see after this section. Let's see, number 34. We have another exponential equation. This time the base is e on the left-hand side and 7957 on the right-hand side. That's number 34, e to the 1 minus 8x. Okay, so again, whenever you have an exponential equation, your first look is to see if you can create the same base. But when it's e, it's probably not going to happen. So here we want to use the same approach we used in number 28, except whenever you see e, that's a really good clue. You don't have to, but it's a really good guide that you're going to use natural logs, right? If you had base 10, you'd want to use log base 10 because of the special properties, right? Sometimes it'll just make it really a lot easier. So let's take natural logs of both sides here. Okay, now the left-hand side, if you notice, is one of those special properties we had talked about earlier. this one, right, which goes along with the any base. Right, these are really the same thing. This one is just with a base of e. Right? If we put log base e of e to the x, that's what we're looking at here. Right? So that's what we're looking at here. This is the exponent, 1 minus 8x. So we have the natural log of e raised to an exponent. Natural log of e raised to an exponent is just that exponent. So the left-hand side is just one minus 8x. And now again, just a nice linear equation. We know how to solve linear equations. We isolate the term with an x in it. This is just a number. This thing is just a number. We plug it into the calculator. We subtract 1 from it, extract 1 from both sides. And then we're going to divide by -8. So plug that into the calculator, please, and see what we get there. Just drink my coffee before it gets cold.
So it's 0.998.
Point?
Yeah.
All right, that's close enough, right?
Is it negative?
Huh?
Let me see if it's negative. Can it be negative?
What'd you get? What's this number?
8.98.
So 7.98?
Yeah, that's negative. Then.
So negative, okay. Thank you. And again, easily checked. Put this back into the original equation and make sure you get a correct answer. All right, so that is, again, an example of taking logarithms of both sides of the equation, the original equation, breaking it down using a special property of logs to make this side equal to this. And then once we get to this point, it's just a linear equation. We isolate the x, we plug into the calculator, and we get our solution. All right, so we talked about change of base. We talked about taking logs of both sides. Another approach using logarithms to solve exponential equations is as follows. At number 52. Actually, 52 is one we pretty much just did. Let's look at number 54. 54, page 490. We have another exponential equation. This time it's log base 5. Oh, I'm sorry, this is a logarithmic equation. So let's see, are there any other exponentials we want to look at first? Let's do one more exponential and then we'll go to logarithmic equations. Let's see, another method I want to make sure that we cover here. We did same base, we used natural logs. I guess that's really the only two cases. Let's do one more just to solidify. So let's look at something like this. We have 5 raised to the x minus 2 equals 4 raised to the 2x plus 3. All right, so this is an exponential equation. And again, our first choice, what do? We look for a same base, but 5 and 4, there's no way we're going to create a same base for 5 and 4. So our next approach is to take logarithms of both sides. Let's take natural logs. Again, it doesn't matter, you can take natural logs or log base 10. But those are the only two choices, again, because those are the only ones we have on our calculators. So we take natural logs of both sides. And then again, we're going to use the power rule that I had up earlier, and take the exponent and put it out in front of the log here, take the exponent and put it out in front of the log here. So this is really no different than what we were doing. It's just a little bit more involved because we have a binomial term on both sides of the equation. We have x in two different places. But this is just a linear equation now, no big deal. We distribute, again, this is just a number, right? Natural log of 5, it's just a number. Natural log of 4, it's just a number. So we want to multiply it out and then gather the x's on one side of the equation, isolate the x, solve for x, right? Just like any other linear equation. So this times x, we get x times natural log of 5, minus 2 times natural log of 5, and over here, 2x times natural log of 4, and 3 natural logs of 4. All right, so you just got to be careful. There's just a few extra steps here, but just pay attention to detail, do the little things, gather the terms with x's. So we got this has an x in it, and this has an x in it. So we want to put those on the same side of the equation and put everything else on the other side. Doesn't matter which side. I'll bring this and this to the left-hand side, so the x ln 5 stays where it is. We're going to subtract 2x ln 4 from both sides, and then I'm going to add 2 ln 5 to both sides. So we still got the 3 ln 4, and now I'm adding 2 ln 5. So again, this is just a number, that's a number, this is one term, and that's another term. So now we have everything with an x in it on one side of the equation, so I can factor the x out of those terms. So I take an x out of this term, I'm left with the ln 5. I take an x out of this term, I'm left with 2 ln 4. So I get ln 5 minus 2 ln 4. And over here we just have numbers 3 ln 4 plus 2 ln 5. One more step, we divide both sides by this number here to solve for x. So we get 3 ln 4, 2 ln 5 over ln 5 minus 2 ln 4. And we used ln so that we could punch it into our calculator and get a result. Sometimes you'll be asked to leave your answer with logarithms. If that's the case, then you just leave it like this. If you want to check your answer, which is always a good idea, you can get the number itself and plug it back in and make sure that it's true.
Negative 6.34.
Thank you. All right, so if we did that right, put that back in here, and we should get a true statement. I'll check all these later to make sure they're correct. All right, so we've covered exponentials pretty solidly, I think. So now we're going to go to logarithmic equations. And we created some actual logarithmic equations in dealing with the exponentials. But we have some other cases. So any equation that involves logarithms, we call a logarithmic equation. So basically we're going to use two ideas to solve logarithmic equations. We're going to use the one-to-one property, one-to-one property of logarithms, which says if I have a logarithm base b of something on one side and I have a logarithm base b of something else on the other side, well, pretty obviously those somethings have to be the same. Right, so that's one property that we're going to use. And then another property that we're going to use to solve these is what I put up earlier about the relationship between exponentials and log form. So sometimes we can take the log form and change it to exponential form and it becomes easier to look at, or vice versa. All right, so here's the base, and the exponent is x, and the result is 1. All right, so using, this is pretty much a definition of logs versus base exponential form, I should say. Exponential form. All right, so let's look at a couple of these. So we're 52. So one I was just going to do earlier. All right, so this is number 52. page 490. And we have a logarithmic equation. And again, we'll start with a pretty easy one. Logarithmic, natural log of x equals 3. Okay, and we want to solve for x. So we're going to use this idea to change from the given log form to exponential form. Okay, so sometimes that's a good first thing to look at. Change it to log to exponential form and see if it's easier to deal with. So we know here this is log base e, right? So using the definition, we know this is the same thing as, okay, this is equal to a base of e raised to an exponent of 3 equals x. That made it a lot easier, right? Now all we got to do is plug that into the calculator and see what e raised to the 3rd power is. I might even have that here. I do, don't worry. That one is going to be negative 20.09. And again, you can always check that. Put, I guess we just checked it by raising e to the 3rd, making sure that we got that number. Nothing really to check there. You could take the natural log, actually you could take the natural log of this number and you should get something very close to 3 if there wasn't much rounding going on there. All right, so that's an example of using the definition. Let's look at another one, a little bit more involved. Number 56. Let's look at number 56. Is that the one? Yes. 56 is another logarithmic equation. Logarithm base 2 of x plus 50. And that equals 5. So same idea here. First, obviously it's not, there's not 2 logs. If there's 2 logs involved, then this is generally kind of what you're going to look at. You're going to try to set up this if statement. If there's only one logarithmic expression involved, then this is probably what you're going to look at first. So we looked at this one again, 1 logarithm, so we changed it to exponential form and solved it. Same thing here. There's only 1 logarithmic expression, so let's change this to exponential form. The base of 2 raised to an exponent of 5 gives a result of x plus 50. 2 to the 5th equals x plus 50, and this one's pretty easy. I got the answer for this one, don't worry. So here, 2 to the 5th is what, 32? And then if we want to solve for x, we just subtract 50 from both sides, and we end up with our answer. Okay, so if you put that number in there, you'll see negative 18 plus 50 is 32. 2 raised to the 5th is 32. So we know that one is correct. So that was using the relationship between logs and exponents. Again, so let's look at one where we use that one-to-one property. So now we're looking at, let's say, number 74. Again, page 490. Number 74, we have 3 times log base 2 of x minus 1. And that's going to equal, when I say 74, 5 minus log base 2 of 4. Okay. So that is quite obviously a logarithmic expression. So when you have more than one, now this one, there's a couple ways to look at this. If you notice that this is just very easily calculated, right? Logarithm base 2 of 4. We're saying what exponent goes on 2 to get 4. So we know this number is just 2, right? So let's do it that way just to make this easy. Then we're back to where we were, right? So we'll do this one just since it's up here. We'll do another one where that's not the case. But when you notice something like this, this is one of our special properties. This is logarithm base 2 of 2 raised to the 2nd. Therefore, our answer is just the number 2. So we can now rewrite this as 5 minus 2. Now we're right back to where we were before, so this one isn't a good example of the one-to-one property, but we'll do another one. So now we solve this, we isolate the term with the log in it, so we'll divide both sides by 3. 3 divided by 3 is 1. So now we have log form. We're going to change that to exponential form just like we did in the previous couple examples. Here we're saying 2 raised to an exponent of 1 equals x minus 1. So 2 raised to an exponent of 1 equals x minus 1. Easily solved. We add 1 to both sides and we get our answer. Now, something I haven't mentioned here, for logarithms, again, if you recall, when we looked at logarithms, we said the domain was only non-negative values, right? When we have a log function like this, the domain is only positive, well, non-zero, and actually positive. 0 is not included either. So it has to be positive. So you got to check these answers and make sure that this value is not 0 or less than 0. If your answer gives you the logarithm of something less than 0, then it doesn't exist, right? But we're okay here because the 3 goes in here and gives you a 2, which is okay, right? But check your answers for logs. If we came up with 0 here, we couldn't accept it because then we get the logarithm of -1, which does not exist. Okay, so very important to check your answers when you're dealing with logs because of that restricted domain. All right, so still we got to look at one that has the one-to-one the one-to-one property. Let's look at number 76. Same page. You got logarithm base 2 of x minus 3 plus logarithm base 2 of x minus logarithm base 2 of x plus 2 equals 2. All right, so this one obviously a little bit more involved than the other ones. We got 3 logarithmic expressions here. So we have to remember our properties of logs. So you can deal with this in a couple of different ways. You can gather these 2 logs together and use the product rule in reverse, right? Logarithm of something plus log, it has to be the same base. These bases are all the same. So this is the product rule. We can combine this into one logarithmic expression. Remember, condensing. So this would be x minus 3 times x. Or you can look at it this way and combine those 2 first. It really doesn't matter which ones. Subtraction, remember, is the quotient rule. We would have the logarithm base 2 of this divided by this. So either way you want to look at it, eventually you're going to end up with the same things. Let's look at it this way first, where we combine those 2 terms. So using the product rule from our previous section, we're going to get logarithm base 2 of x minus 3 times x minus logarithm base 2 of x plus 2. Okay, so we just combined the first 2 terms using the product rule to get the logarithm base 2 of that product. So let's multiply that out, see what we get. So x squared minus 3x minus logarithm base 2 of x plus 2. Okay. So actually this isn't a good example of one-to-one property either, but it's a good example of a logarithmic equation. Again, we're gonna now combine those 2, the difference, right? Logarithm base 2 of this minus logarithm base 2 of this, using the quotient rule. I can now combine into one term, one logarithmic term, using the quotient rule to combine these 2 into numerator over x minus 2, and that's going to equal 2. And now we're back to where we were, right? This base raised to this exponent gives this result. Let's see what we end up with there. That base raised to that exponent gives us this result. And now we got to go back to chapter 1 and remember how to solve rational equations. This is an example of a rational equation, which we know how to deal with. This is just the number 4, so we get this rational equation. So we want to get rid of both of the fractions, right? So we're going to multiply both sides like we did in section 1.2 or 3. We multiply both sides by the least common denominator. There's only one denominator here, so we multiply both sides by x plus 2. So we get 4 times x plus 2 equals x squared minus 3x. We see we're going to end up with a quadratic equation here. Let's distribute the 4. Let's gather everything on the right-hand side and put 0 on the left-hand side to get our nice standard form. We're going to subtract 4x from negative 3x, and we're going to subtract 8 from both sides. And now nicely, we get a quadratic that can be easily factored into two binomials. Looks like 8 and 1 are going to work. We want negative 7 in the middle, so we're going to put negative 8 and plus 1. So we get two possible answers here. We get an x equals 8, and we get an x equals negative 1. So this is where checking your answer again comes into play. The 8, you go back to the original equation. 8 minus 3 is positive, so that works. 8 is positive, so that works. 8 plus 2 is positive, so that works. So 8 is a viable answer, but negative 1 isn't going to work, right? Negative 1 gives us a negative value here, a negative value here, positive value there, but that one's no good. So we can't accept that answer, and our only answer is x equals 8. All right, so we still haven't gotten a good example of the one-to-one approach. So let's make sure we get at least one of those. But that was probably the more difficult, most difficult one you're going to see dealing with logarithms. We did that. We did the definition of logs. One-to-one property. Here we go. All right. How about this one? Let's say we have natural log of x minus 3. This is checkpoint 8 on page 486. We have natural log of x minus 3 equals natural log of 7x minus 23 minus natural log of x plus 1. All right, another logarithmic equation, this time 3 separate logarithmic expressions. So remember the one-to-one property says we want logarithm, natural logarithm of something on the left-hand side equals natural log of something on the right-hand side. So if we combine these two using the quotient rule, then we'll have the if statement of the one-to-one property. So this doesn't change. Now over here, using the quotient rule, because it's negative, we're going to get the natural log of this numerator over this denominator. Right? So that's the quotient rule. Now we have the one-to-one property. For this equation to be true, right? For this to be true, well, this has to equal this, right? This part here has to equal this part here. So now we're pretty similar to what we were just looking at. We're going to end up with a quadratic equation. It's a rational equation. Once we multiply both sides by the x plus 1, we're going to get a quadratic. So we multiply both sides by x plus 1 to get rid of the fraction. And again, we're going to have a quadratic equation here. We'll multiply this out, x squared, we get minus 3 and plus 1 for the middle term. We're going to gather everything onto one side. Let's make it the left-hand side since we got the positive x squared over here. So we're going to subtract 7x from negative 2x. We're going to subtract 23 from negative 3. Oh man, is that right? 26. That's 13 and 2. We can't get a 9 out of that. Looks like we're going to have to use the quadratic formula. If I did everything right, let me just make sure I copied everything right here. X minus 3, 7x minus 23, and x plus 1. 7x minus 23 over x plus 1. That looks good, right? Anything else I'm missing here? 2 times 13. No other number goes into 26, right? I don't think so. I got whole number answers here is what's confusing me. If we got a whole number answer, then we should be able to factor it. And I copied it all right. 7x minus 23 over x plus 1 equals x minus 3. Did I do that right? X squared minus 2x minus 3. 7x minus 20. There we go. I thought there was a mistake in there. Okay, so now we're going to add 23, which is going to make this much easier to deal with. Adding 23 to 3, and now we can factor it easily into two binomials. 20, we need factors of 20 that are going to give us a 9, so 5 and 4. For the signs, we want negative 9 in the middle, positive 20 for the product, so we're going to put negative on both of those. And we're going to get our two possible answers before we check. 5 and 4, we go back to the original. 5 works here, 5 works here, and 5 works here. 4 also works, also works, also works, so we get two possible answers. Okay, let's do one applied problem, and then we can call this section done. All right, so let's look at number 104. And this is just using any one of the methods to solve a word problem, basically. So this is number 104 on page 490. And it says the formula is given here for the population of Texas in millions T years after 2010. So this is the population of Texas in millions, 0.0187 T. All right, so this is the population of Texas X years after, or T years after 2010. So 2010 is T equals 0, and so forth, right? All right, so that's the model, that's the formula that models the population. So the first question, two questions. What was the population of Texas in 2010? So that's what this is here. And then our first question is what was population in 2010? So we just decided here that if this is true, which it is, that's given information, T is the years after 2010. If we're looking at 2010, then all we got to do is put T equals 0 into this equation. So basically we're looking here at A as a function of T, just like F as a function of X. We're saying A is the population as a function of time using this equation. So our A at 0, right, for 2010 is just going to be 25.1 times e to the 0. Right? Anything times 0 is going to be 0, and we know anything raised to a 0 is going to be just the number 1. So our answer is 25.1, and we remember that it's in millions. Right? So this is just evaluating an exponential function. Right? We did that earlier. This is just, instead of just being given the function and asked to evaluate it for an input of 0, we're given a situation. It's the population of Texas T years after 2010. We're answering the question by evaluating the function. And then the second question says, when will the population reach 28 million? So question 2 here, when, and when you're asking when, you're saying for what t, right, for what t value is a of t going to be 28? And again, we know it's in millions. So now, again, we're just forming an equation, but this time, instead of being given the t value, we're being given this value and asked to solve for t. Okay? So here we're saying when is the function equal to 28 for what t value? 0.0187 t. Okay. So that's the question, and that leads to this equation. It's a one variable equation. It's an exponential equation. So we go through our methods for exponential equations. We want to isolate the term that has the unknown in it. So we'll divide both sides by 25. And now we have that nice setup where we can take the natural log of both sides of this equation. Natural log of 28 over 25. Just plug that into the calculator and get a number. Natural log of e raised to anything is just that, anything. All right, so now we get natural log of 28 over 25 equals the exponent here. And then finally, we put natural log of that number is the numerator. We divide by 0.0187. And let's see, do I have an answer here? I don't. What is it?
6.06.
All right, so that's a little bit more than 6 years after 2010. So 2016 or so, a little bit into the year 2016, according to that model. If the population was 25.1 million in 2010, and it's growing at this rate, which we'll get to in the next section. Solving that equation gave us a little bit more than 6 years after 2010, so our answer is the year 2016.